Okay, I think we'll start. So welcome for the tutorial number 3. We will talk about Lightning Network and off-chain transactions. My name is Mariusz Nowostawski. I'm an academic, a computer scientist. I work in University of Science and Technology in Norway. I work together with Rene. Rene is supposed to be here with me today to give the more technical part of the talk. But he is in a hospital for a minor surgery, and he will be out in 2 weeks. So he couldn't travel, so you will only have me. If he was here, he was the technical person developing the ideas and making sure that we're building it right. And I'm more of an academic, I'm more of the high-level person trying to figure out if we are building the right thing. So if we were both here, we would kind of complement each other. Because I'm only alone, then you'll only have one-sided perspective on things. So what this tutorial is about? We will talk a little bit about the basics, and then we will talk about RSMCs and HTLCs, about the invoices, and so on. So there is a lot of technical jargon and a lot of technical topics. So before we dive into that, let me try to explain what Lightning Network and off-chain transactions are, just waving my hands. So how many of you know what is Lightning Network? And have any of you used it? Have any of you sent transactions? Great. So most of you don't know. So how many of you used cryptocurrencies and sent transactions through a blockchain? Kind of same people. So if you were to send somebody bitcoins, you would have to write a transaction and then put it into the ledger. And immediately once you've done it, another person would have the funds because they can spend the output of my transaction, which is in the ledger, right? That's how the Bitcoin blockchain works. That I'm preparing a transaction, I'm signing it, I'm proving that I can spend somebody else's output, and then once I've done it, I have this transaction signed, ready to go into the ledger, and then I do this. I put this into the ledger, and then the funds are yours, okay? So imagine that I have this transaction in my hand. I haven't put it into the ledger yet, and then I gave it to Bob, and I told Bob, look, here is the transaction. You can put it into the ledger at any time. The coins are yours. I own you 1 Bitcoin. Here it is. How many transactions are in the ledger now? None, because Bob hasn't put that into the ledger, and I haven't put that into the ledger neither, right? And I paid Bob 1 Bitcoin, and nothing is visible in the Bitcoin blockchain, and nothing happened yet. And let's say 2 weeks later, Bob owns me 1 Bitcoin, and he says, oh, look, Mariusz, I own you 1 Bitcoin now, but I have this one from you from last week. I will give you back. And he gives me back this 1 Bitcoin transaction which I gave him. And now I paid him once, and he paid me once, and how many transactions are in the ledger? 0. We haven't put anything in the ledger yet. And that's basically the basic idea, right? The basic idea is that we can trade, we can do transactions without actually using the ledger if we use mechanism like that, if we use a mechanism of IOUs. So the concept is extremely simple. It's extremely trivial. What's not trivial is that, you know, Bob doesn't really trust me, and I don't really trust Bob, right? So when I gave this transaction to Bob, Bob has my Bitcoin, but if I create a new transaction which spends the original output and put it into the blockchain, then Bob lost his money because now his transaction is useless, right? So, and then if he paid me back, he said, Mariusz, here is your transaction back. And I destroyed it. I said, okay, great, thanks, Bob. But he didn't delete his copy. And a few days later, he puts it into the blockchain. It's still a valid transaction because I have signed it, right? Then I lost my money. So the complexity of this off-chain transactions is that we have to make sure, we have to guarantee that I will not cheat Bob and Bob will not cheat me. And one way of doing it is what I will describe in this tutorial. And if there are any other ways, that's great. Maybe we haven't come up with those yet. But I want you to remember the kind of the basic concept of off-chain transactions is that those are transactions which happen in a way, in a peer-to-peer fashion without involving the ledger. And it kind of brings a little bit of a philosophical concept of what the ledger is. So let us start with a blockchain talk about cryptocurrencies, the original announcement from Satoshi about he's working on an electronic cash system without no trusted third party. And the idea is that it's kind of like, as he says, a peer-to-peer electronic cash system. Peer-to-peer cash, right? We can send money in peer-to-peer fashion. So if you think about it, we use blockchain to achieve that by sending the transactions into the blockchain. The scenario that I explained initially, that I'm preparing a transaction, giving it to Bob, and then Bob giving me a transaction, that's also kind of a peer-to-peer. I'm actually directly interacting with Bob without interacting with Ledger. The only reason why we're interacting with the Ledger is because we don't trust each other. It's kind of a trust replacement. So we're using the Ledger to solve the trust problem, not the peer-to-peerness problem, right? A purer system for cash, peer-to-peer cash, would be if I can pay directly to Bob without involving anything extra. So kind of, if you think philosophically about it, the blockchain is kind of not really that peer-to-peer. I have to put something into the ledger. I'm not directly talking to Bob, and I'm not directly sending something to Bob. We're using the ledger to solve this kind of a trust issue. So if we think of off-chain transactions as happening kind of off-chain, off the ledger, and the ledger being kind of a trust repository, then we can think of the ledger as a court system to resolve issues if somebody violates the trust, right? So coming back to the original idea, I'm paying Bob this 1 Bitcoin, and then in case I'm gonna cheat him, or in case he wants to cheat me, we refer back to the ledger and resolve who is cheating whom, right? So the idea is that we're not using the ledger to send transactions to each other. We're using the ledger as a conflict resolution mechanism, as a court system to solve trust issues between me and Bob. So if you look at it at the ledger in this perspective, then off-chain transactions can be treated as a purer form of peer-to-peer payment. And then we use the blockchain as a kind of a court, as a resolution mechanism. Either way, if we treat the blockchain as a resolution mechanism or as an actual direct payment system, we have the scalability issue, and that has been known since the beginning. So here it is highlighted that, great, nice idea, but the system will not scale. It will not be able to process the amount of transactions that we need to deal with. So the notion of the ledger being a mechanism for doing peer-to-peer transactions is nice. It doesn't scale. So the other idea of using kind of direct payments scales because it doesn't involve anybody else. It doesn't involve the ledger. It involves the ledger because of the technology that we have to use. But conceptually, if we have a solution which doesn't involve the ledger, then it would kind of be better. All right, so what is a Lightning Network? So it is a kind of an attempt to turn a Bitcoin system into an electronic cash system. So normally Bitcoin cannot be used for microtransactions, cannot deal with the volumes of transactions that we would like it to be used for. So we need something else. We have to have layer 2, say, mechanisms to solve the transaction issue. We want to be able to have an arbitrary number of transactions. If my transaction to Bob is completely independent from your transaction to Alice, then they can happen at the same time and they can happen instantaneously. So the system will scale. So is the hope. To get kind of a currency properties So Bitcoin is a good store of value system because as a store of value, it doesn't need to have those kind of fast transfer timings. But if we want it to be more like a cash system, we need something else. There is an improvement in terms of anonymity because Bitcoin, even if used properly, where each and every single transaction generates a new address, it's still traceable. All the transactions are still visible in the chain, and you can follow the money flows. People are trying to use mixing services and trying to kind of use some additional anonymization techniques, but it doesn't work that well. Yeah, so a small digression. In the first tutorial, which was really good, a speaker mentioned that the hashes sometimes are not treated as a good mechanism to prevent GDPR violations. Yeah, that is true. There are some caveats to that. So if the hash is used multiple times and you can track the usage of that hash, that would violate linkability under GDPR. But if the hash is only used once for a particular document, then this document hashing to the hash doesn't leak any additional information, and that from the law is fine. So a single-use hash would pass some of the GDPR checks. Reusing the same hash multiple times in the ledger wouldn't. All right, so we have some additional properties. So, for example, in current system, if I pay Bob, and then Bob pays me, that's visible in the ledger. We can see that that happened. Maybe that's not of anybody's business. Maybe if I paid Bob and Bob paid me, like why should everybody see that that happened? So some things can be treated off-chain and can enhance some of the privacy related to transactions. Yeah, by the way, if you have any questions at any point in time, just raise your hand. I'm very happy to stop talking and answer questions. So don't hesitate to stop me and ask questions. And those people who know about Lightning Network or anybody else, if you hear me saying something which is wrong, just say it. Just raise your hand and say that's not correct, okay? So what are the building blocks for Lightning Network? What are the building blocks for making this scenario with Bob kind of possible? So one of the building blocks is we have to have a channel which basically keeps track of those IOUs, who owns how much whom, right? So if I want to send Bob 1 Bitcoin, we have to have a channel which records that now my balance is 0 and Bob balance is 1 between us, right? And we have to agree to that. And then if Bob pays me 1 Bitcoin, then his balance will be 0 and my balance will be 1, right? So depending how the channel is funded initially, let's say the channel is funded by both of us, me and Bob putting 1 Bitcoin each. So then the initial state of the channel is that Bob account is 1 and my account is 1. If I paid Bob 1 Bitcoin, then his account is 2, my account is 0, right? So this sequence of IOUs, we have to keep track of that. And to keep track of that, we need this channel. And we want a channel to be duplex because we want me being able to pay to Bob and Bob being able to pay to me. Initial ideas behind Lightning Network were to use unidirectional channels, which means I can pay Bob and then we have a separate channel for Bob to pay me. There were some disadvantages of this solution. One being that once I used up all the initial funds that I had, let's say I founded a single directional channel to Bob and I said initial status, I have 5 Bitcoins, Bob has 0. And if I used it up, if I already paid Bob 5 Bitcoins, then this channel is useless because I cannot pay Bob anymore anything. So we have to dismantle this channel and Bob has to claim this 5 Bitcoin. But if we have a duplex channel, we can basically continue changing the IOUs between us indefinitely. Can if I have a channel of capacity 10, so if I put 10 bitcoins into the channel and Bob put 10 bitcoins into the channel, can I pay Bob 20 bitcoins? No, I can only pay up to the capacity that I have in the channel. Yeah, we will talk about those terms a little bit later. We also, so we will talk a little bit about the penalties later as well. Okay, so those are the all the building blocks for making the entire network. So first one is the duplex channel. The second one is we have to chain how I'm gonna pay to Alice if I don't have a direct connection to Alice. So if I have a connection to Bob, I have a channel to Bob, but Bob has a channel to Alice, then I should be able to pay Alice without having a direct connection to Alice, because we can reuse the IOUs ledgers between our pairs, right? So if the state of accounts is I have one, Bob has one, between me and Bob, and it's the same between Bob and Alice, then if I want to pay Alice one coin, the state between me and Bob now is Bob has 2, I have 0, and between Bob and Alice is Bob has 1 and Alice has 2, right? So we transfer the IOUs from me to Alice by modifying 2 channels, 2 IOUs that we have between each other. And then we need, the third thing is to kind of tie it together is we have to have protocols which are for finding the routes, for maintaining the IOUs, and for advertising of what is happening in the network. So we need kind of those 3 building blocks to have a solution which is based on this simple idea for off-chain transactions. So we will spend the first part discussing how to do the channels, how to do this initial thing, which is me and Bob can have an IOUs where I can pay Bob and Bob can pay me as many times as we want, indefinitely, up to the capacity of the channel without leaving any trace in the blockchain proper. We will just maintain the state of those IOUs, okay? So the purpose is to have an ability for instantaneously changing the state of the IOUs between me and Bob. So how does that happen? It happens sort of through internet communication, but it happens off-chain. Nothing has to be logged in the blockchain, and nothing needs to be approved, and nothing needs to be validated. I'm just sending messages to Bob, and as soon as this exchange happens, then it's done. So we are bound by the communication channel between me and Bob. It can be arbitrary fast, and it can happen, arbitrary fast based on the laws of physics and the networking speeds that we have. We want the system to have a property that I don't need to trust Bob, that if Bob tries to cheat me, the protocol will detect it and I will get my funds back. So if let's say I paid Bob 1 coin and Bob sees that I'm trying to not to spend it somewhere else or do something, against the protocol will kind of detect it and punish me for trying to do that. And then if there is a conflict, then we will have to settle it using the normal blockchain ledger. We can have no fees. So currently the Lightning Network has kind of a fee system built in. But in theory, we could agree with Bob that we're going to pay each other without fees. So between 2 partners, how the payments happen is kind of up to the partners. They can have no fees for doing that. Payments can go back and forth, as we described. And the idea is that we have scale it. So Rene is using kind of a comparison to HTTP. So as you know, HTTP is, hypertext request response protocol, which is used for sending documents over the World Wide Web network. So a client requests a document, a particular web page, or a file from the server, and then the server sends it back. So that's the kind of the normal usage of the protocol. But as time went on, we've realized that it's kind of nice to be notified from the server side that something happened. But the protocol doesn't allow that, at least not the original one, HTTP one. So we kind of abused the protocol. We used some mechanisms for pretending that the server can notify something to the client. So in similar spirit, yes, so that's more description of how the push notification happen over HTTP. The idea is that in the same spirit, we kind of abusing the mechanisms of Bitcoin to achieve something that Bitcoin was not designed to achieve. Bitcoin was, I want to pay you, therefore I prepare transactions and pay you. But now instead, we want to have a mechanism which says, you want me to pay you. You want to issue me an invoice which I will pay when I want to actually transfer the funds. So instead of being kind of a payer-initiated protocol, we want it to be payee-initiated protocol. So we kind of abusing the Lightning Network specification, is abusing the protocol to achieve that. So Bitcoin is not a request-response protocol. It's rather a broadcast gossip protocol. So we're broadcasting messages, we're broadcasting the blocks that we found, we're broadcasting the hops that we know about. We kind of just achieving consensus and achieving voting by broadcasting messages. So what we want is we want to change the mechanism in such a way that normally when I pay something through a transaction, I'm specifying to whom the output, who can claim the output. I'm either putting a public key or a hash to a public key into the output. Therefore, once the transaction is in, it's kind of spendable by whoever owns the output. What we want to postpone the decision who owns the output until later in time. And then abuse the protocol by doing double spending and changing who can claim the output. So we subsequent transactions will kind of change to whom or how much the output actually goes. So the analogy is kind of turning the roles around and changing the sequence of the protocol a little bit. So to achieve that, we need something which is called 2 out of 2 multisig, which is relatively easy to achieve because in Bitcoin we have something which is called pay to script hash. So the script can generate the logic of how the funds are released in the UTXO. So from the previous tutorial, you've learned how to use UTXOs for various things in the financial sector, and Bitcoin is used for transferring the value of the content of the Bitcoin transaction to somebody. All right, so then we have this concept of smart contracts or contract in the Bitcoin transaction. It's not really a contract per se, it's kind of a script, and it basically is a transaction which requires 2 signatures to be valid. So if we want to spend it, if we want the funds to actually go somewhere, we have 2 participating stakeholders have to sign the same transaction. They have to provide kind of a signature which unlocks the funds. So it is a form of pay-to-script hash that existed before, that existed for a long time in the Bitcoin blockchain. We will talk a little bit about the format of the addresses in a moment. The necessary component for this to work was a change in the description of the transactions, which allows maintenance of the transaction ID if certain parts of the transactions are changed. So the original Bitcoin protocol you could modify some of the details of the transaction, which would not change the actual transaction. It would still spend the same coins from the same inputs to the same outputs, but it would change the transaction ID, the hash of the transaction. And that's called transaction malleability, which means somebody can issue kind of a copy of the transaction with all the signatures being kind of the same, but with a different transaction ID. And that complicates the process of tracking for double spending or for tracking certain enforcements of the protocols that we are discussing here. And that happened in August 2017, where the Bitcoin core developers decided to do a soft fork introducing segregated witness. And that kind of allowed some of this technology to be plausible. So I will dive a little bit into those details in a moment. So they describe the mechanics of how this actually happens. And to understand that, we have to do a little bit of a detour into Bitcoin scripting. So in the previous tutorials, you've been kind of introduced to blocks and to blockchain, to Merkle trees, to transactions, kind of on a high level, but not really to the Bitcoin scripting. So it's kind of nice because that's the part which I kind of prepared. So a block header, yes, you know that more or less. So we have a version, we have the hash to the previous block, we have a timestamp of when the block was generated, the difficulty, this number of zeros in the hash that was in the previous tutorials as well. And then we have how many transactions are there, and we have the hashes in the Merkle tree of all the transactions, right? I will not ask you what is a Merkle tree. That has been introduced before in the previous tutorials. I will ask you what's DAG. Who knows what DAG is? Yeah? Directed acyclic graph. And why it is useful? What do we use it for in Bitcoin? For transactions, for the UTXOs, right? So the entire Bitcoin transaction system is based on the directed acyclic graph. Great. So we can have a look at the particular transaction. So here I already clicked on the link. So we see what we just learned. We have which block this transaction was included in. This is the input address. Those are the output addresses to where the funds will go. And we have the scripts. So what are the scripts? Well, one kind of unlocks the previous outputs. So I have to provide data which allows me to spend funds from that output. And then the second one provides details of how those two can be spent. Who can claim the money on those two outputs, right? So you have kind of money coming in and money coming out. What happens if those numbers don't add up? Come on. The miners take it, right? So if those numbers don't end up and the first one is larger than the second one, then the miners will take the difference. If the first one is smaller than the other one, the transaction is rejected because it's invalid. It tries to spend more than flows into it. If the numbers do add up, what happens? The miners may not mine it because there is no fees attached to it, right? Therefore, the miners will say, screw it. We're not going to put this transaction into the block because you're not paying us any fees. Or the miners might be good-hearted and they will do that. The current protocol kind of rejects transactions which don't have fees included. So the nodes which pass messages around and say, let's announce this transaction into this mempool for the miners to mine, they actually, the default behavior of the client is to drop those transactions which don't have any fees attached. So it's actually very hard to kind of mine transactions with no no fees. But how can this be done? How can you mine transactions with no fees? Sorry? Yeah, you can be attached directly to a miner or to a mining pool, and then you gain your rewards from the mining work anyway. So as part of your transactions, you can include transactions which have no fees. So in the mining pools, you often will see transactions which distribute the funds to kind of participating nodes, and those transactions often don't have any fees attached to them because the miners include them, pro bono into the block as part of the mining. Great, so we have seen a transaction. So what else is interesting? The interesting bit is the script thing. So what is the script? The script is a simple language to do operations which involve checking the hashes, which involve hashing some public keys, which involve checking the conditions of how to spend the coins, right? So in the original very simple case, we have to check if whoever wants to claim the funds actually has the right to spend this output. So we have to check two things. One thing is for this transaction, for example, we have to check. So if someone wants to spend this 3.33 bitcoins, right? So someone wants to spend this. What is that we have to check? One is that we have to check if the public key, which they use to spend this, matches the public key of this address. So we have to do a comparison. We have to compare, okay, your public key and this key, which is in this address, match, right? But that's not sufficient because I could provide this public key and match it myself. What is the second condition we have to check? Come on. We have to check the signature as well. And what does it tell us? This tells us that whoever signed this message has access to the private key. And we consider anybody who owns the private key to own that address, right? So we use the private key ownership as the de facto authorization for spending the funds. So we're checking two things. We're checking the signature, which can only be generated by somebody owning the private key, and we're checking the public key, that it's the same, right? Why we don't check the signature? We could, but for consistency, we're checking both. Yeah. All right, so for doing those two operations, checking the signature and checking the hash of the public key, we need simple operations, right? So for doing that, the original people behind Bitcoin blockchain, they devised this scripting language, which they called script, it's a very innovative name for that script language. And they used forth-like instructions with a stack-based kind of a processing. And by design, they limited the amount of instructions which made it Turing incomplete. It's a very specialized language to do only kind of cryptographic operations and some control flow, but you cannot have, for example, infinite loops in it. So what is the fundamental data structure in Forth? How many of you programmed in Forth? Nobody? All youngsters? I did some programming in Forth. A couple of years ago, there was a student in Australia, actually, who was later moved, no, in Canada, not Australia, who devised a kind of a language which was factor-based, or Forth-based. It was called Factor. It was kind of a modern reincarnation of Forth, and it was quite fun to use it. So how many instructions do you need to make something Turing complete? If you were to design a virtual machine, how many instructions would you need to have it Turing complete? How many? One. Perfect. Very good. It would kind of include a control flow, an arithmetic, and a logic in a single instruction, and then you can express anything with this just one instruction. All right, so we look a little bit into the transaction. So you will notice that it has kind of a field called lock time. So this transaction cannot actually take effect until this lock time field is fulfilled. It's a little bit of a joke. So we're kind of diving into some of the technical details of how it works. And I'm asking you about virtual machines. I'm telling you about Forth, and I'm telling you about those instructions of the Bitcoin. Why I'm telling you that? We just wanted to learn how the off-chain transactions work. And true, that's very true. I try to spend the first like 30 seconds telling you about the off-chain transactions, but to understand how Lightning Network works and how it actually works on the protocol level, it's unavoidable to dive into those technical things. So with the Bitcoin script, we have two parts. We have the part which blocks the transaction and the part which unlocks it, which allows you to spend stuff. Okay, what is the implication of making the scripting language Turing complete? Well, you would end up with Ethereum, and then you would have a lot of possibilities of writing very generic smart contracts, which are very hard or impossible to be expressed in Bitcoin script. But you also will have to deal with a possibility of infinite loops, of kind of a storage blowing up and so on, and you would have to introduce this gas concept for managing this complexity, for counting how much, or if someone is abusing the scripting to do denial of service attacks on a kind of execution level. The important thing here is that this script has to be executed by anybody validating all the transactions. So it's not only miners who do that work, it's everybody has to do this work if you want to be sure that you're gonna receive the funds that you seem to be having, right? So all the validating nodes and your wallet and everybody who wants to be sure that the funds are really yours have to do this work. So it's a lot of computation if you make it Turing complete to take place, and therefore you have to have those additional mechanisms like you do in Ethereum. So for this simple case, we have a simple transaction with 3 inputs. We see the inputs here, and then we have 2 outputs. So the transaction is kind of ordered and padded with those bytes. And then this is a little bit small, but it basically tracks the output of the transaction A is being used as input in the transaction C. And then transaction D spends this output. And then we have 2 unspent outputs. We have this one and this one, right? So that forms this directed acyclic graph. And we see that those 2 have not been spent, and the other ones have been spent and reused by other transactions. So outputs of some transactions, like for example this one, are inputs of other transactions. So we order them from 0, 0, 1, 2, 3. So here 0, 1, 0, 0, 0. And we reference which one we're using here in this input transaction. So we'll say this input is transaction A, 0th output. Right, so we've already discussed that. And then you have this script, and the script will do all those checks, will kind of encode this logic, and if it evaluates to true, then it's fine. If it not validates to true, that means something is wrong, that transaction cannot be claimed, or this output cannot be claimed. So typical spending pattern is you put a hash of a public key into the unlocking transaction. So whoever wants to spend it will have to provide a signature and a public key, and then the script will execute this logic. So a signature and a public key is needed to unlock the funds. And then, yeah, we've discussed that. And then you have this complete sequence, which basically says here, duplicate the top of the stack. So we have put signature on the top of the stack, then a public key. Then the op duplicate duplicates this. So now we have public key twice. We hashing the first part of the of what's on the stack, and it will have a hash of the public key. Then we're putting what is actually in the script, which is the data for this address. So remember this, we had this in the transaction. So in here we have this data, which is the hash of the public key which we've used. And then we call op equal verify. So we check if this hash and this hash which is inside kind of match. If they match, they are taken out. And then what is left is the first signature and the public key which we put in. And then op check signature happens, which means it checks if the signature is correct on the transaction. And if this script evaluates to true, then whoever is claiming the funds can spend them. So this 3.33 Bitcoin can be spent using this. So this is, yes, this is what I just described, waving my hands. So duplicating the public key, then hashing it, putting it back onto the stack. Then we have this actual public key hash which we've had inside. So now we have those two hashes in. Then we execute verification, and then we evaluate that the signature is correct, and then we have we are done. We have the correct solution, the correct result, which allows somebody to spend the output. So yes, so miners will build the next block. And we've already discussed that. We already discussed in the previous tutorials how the blocks are organized. Miners will take the leftovers from the inputs. So if they have not been spent entirely, those are the leftovers which we were discussing before. And yes, we have the Coinbase transactions, which means they actually don't have any input because they're generating new coins out of thin air. So the miners which find the block, they can generate up to a mining reward number of Bitcoins and use and spend them somewhere. So those are kind of a special transaction. There is one special transaction which basically is a block generation reward. Okay, so this example was using public key hash instead of a public key. Could we just skip all this hashing and just ask the whoever wants to spend the transaction for a public key instead directly, not the hash? And the answer is yes, of course, we could do that. So the script would be much simpler. It would look like this. We're basically saying please provide us with the public key instead of a public key hash, and then the part which checks the signature is kind of, we don't have to hash it, right? So then we have something which is called pay to public key instead of pay to public key hash. Both will work. Initially in the Bitcoin, the pay to public key was heavily used. People were using the public keys directly. But as you see, if we're using pay to public key hash and the transaction has an unspent output, the ownership of that output is unknown because it's hashed. So it's kind of a scrambled. So if someone is kind of checking all the ledger and checks who has how much money unspent yet, they will see the hashes of the public addresses, but they will not see to whom they belong to. If the public key is used directly, you can kind of scan it and see the accounts, the addresses directly in the ledger. The public key is visible once the money are spent, right? So once someone unlocks the input, then they have to provide a public key, which then becomes known. So putting the public key into the transaction to claim and spending it means you are revealing to whom they belong to. And therefore, in the original paper, it was suggested that you should never spend money into the UTXOs reusing the same address. You should be always generating new addresses every time you're doing the spending to kind of obfuscate the trace of the funds. So we have those two output scripts which we have discovered so far. So it's the pay to public key and pay to public key hash. This one is shorter. It's more compact, but it involves more computing. That one is longer, requires less computing, but also leaks information on the entry. It leaks the public key here. This one will leak the public key on claim. And then there is one more, which is pay to script hash. So kind of early on, it was discovered that this ability to send money to somebody using the public key has two limitations. So the first limitation is that we need to know in advance who wants the money on which address, right? They have to publicize this. And second of all, it's kind of the sender which decides, you know, what happens with the funds. What if it is the recipient who wants to decide what happens with the funds when they receive them? Then maybe they want to do something else. Maybe they want the funds to be routed to somebody else's account or do something else. So to do this, what we can do is we can have a script which then hashes to a particular hash and send funds to that script. And whoever can provide the actual details of that script, which hashes to that hash which is in the transaction, then can effectively spend the money. And using this mechanism, we can easily achieve multi-signature schemes. We can do more logic for managing the flow of the funds. Yeah? Good question. So anyone has a suggestion? Yeah? Space, yeah? One? Exactly. So Bitcoin, it was mentioned in the second tutorial that Bitcoin is using SHA-256 for hashing, right? Yes, that's correct, but that's not the whole truth. Actually, Bitcoin uses two hashing mechanisms. It uses SHA-256 and RIPE-MD 160. So if one of those hashing mechanisms is compromised, then the other one kind of doesn't leak the information for a while. And also hashing kind of prevents something obvious. So for example, if I want to hack his account and I know his public key, I can kind of try to brute force it. If I only know hash of his public key, it's much harder to do that, right? It's kind of impossible to even try. Which is a little bit void because, as you say, if it's not reused and the UTXO is 0, then why would I even try to hack it, right? So, but to kind of enhance the security and to save space, it is recommended for reusing the not reusing the addresses. All right, so then what are the revocable sequence? So if we have 2 out of 2 signature, what we can do is let me just see. Yeah. So what we will do, we will try to have a protocol which will reuse the kind of a scripting mechanisms that we have to have kind of this IOU balance being transmitted between us, but having kind of a safety mechanism which allows us to claim certain violations on the using a kind of on-chain transactions. So what we will have is, which is kind of called a revocable sequence maturity contract, which means we have a contract between us that I owe you a particular amount and you owe me particular amount. It's bound by the rules of the protocol, and we can, either party can revoke it if something bad happens. If, like, for example, I'm trying to double spend the funds which I used to, this actually doesn't happen, but if I try to kind of violate the steps of the protocol. And then once we have this, we will kind of update it every time we updating the balance to have the kind of the latest kind of state of the channel. So what we will have is we'll have a kind of a funding transaction which agrees of the initial state of the IOUs, right? So for example, the funding transaction looks like this. It says that we have an input of 100 millibitcoins, and the output goes to both of those keys. So to be able to spend it, we have to have a transaction which is signed by both of the participants, right? So how this money are spent is kind of delayed in the future, because as long as we have a transaction which is signed by those 2 keys, the transaction output can be anything, right? So we have the funding transaction, which output is kind of locked by both of these. And then we have a commitment transaction, which needs to be signed by both. And it says Ali's balance is 70, Bob's balance is 30. And Ali's keys are used to spend this output, Bob's keys are used to spend this, right? It's a very simple, naive way of kind of maintaining the IOU. So if both of us sign this transaction, then Alice can claim this without Bob's key, and then Bob can claim this without Alice's key, right? So this kind of commitment transaction encodes the current state of the IOUs. Clear? It has problems. It will not actually work, but up to this point, it's kind of fine, right? So we have the mechanisms to kind of do this. And then this commitment transaction can be put into blockchain at any time, but it's not, right? This one is, the funding transaction is already locked in the ledger, but this one isn't. We can put it into the chain at any time. And then we are double spending it. So we are updating the balance because Bob needs to pay Alice 10 satoshis. So then, you know, Bob effectively sends Alice the funds by changing the IOUs. He signs this new transaction, and then Alice takes it, signs it as well, and now we have an updated IOU state, right? So now Alice has 80 and Bob has 20, right? And now they can, again, execute it at any time. And this is a commitment transaction too. So what will happen if Alice tries to do this, but Bob put this transaction into the chain before? Well, you know, this wouldn't be valid anymore because this is valid, So therefore, Alice is screwed, right? So we have to make somehow this transaction unpublishable, right? So initially, we have the mechanism to track the IOUs, but we have a problem if Bob goes out of sequence, if Bob publishes an old state of the channel. If there is a new transaction which is newer or updated, and an old one, we have to deal with the situation that Bob tries to cheat Alice out of her money. So we have to change it again. So the first complication is we kind of complicated the normal Bitcoin spending by introducing this double signature at the entry. And then this mechanism is very naive and doesn't work neither. We need to complicate it even further to make sure that Bob cannot do this without punishment or without some sort of detection. So we have to detect the fraudulent publication of old state of the channel, right? So how can we do that? Well, we have to complicate the protocol somewhat to give Alice a guarantee that if Bob tries to publish something before something outdated, so the state of the channel which is actually invalid, she has a mechanism to kind of punish Bob for that. And this mechanism is revocable and bridge remedies that we will have. So we will make it impossible for Bob to claim the funds before Alice has a time to react and kind of say, wait a minute, what Bob just published is out of date. Actually, I have something which I can spend those funds earlier before Bob, right? So if this situation happens, if Bob publishes a state of the channel which is outdated, Alice needs to have a mechanism to spend, to spend Bob's 30 micro bitcoins before Bob can claim them, right? So what we want is we want those to be time locked. So if someone wants to claim it, the other party can actually use a different transaction which spends this output before Bob can spend it, right? So we're complicating the steps by a second level and by introducing something which happens here. So those two cannot be used directly, immediately. They can only be used after a bit of a delay. And this delay is different for Alice here and for Bob here. This delay here is longer than Alice can claim if something was out of sequence, right? So we need two more transactions. So one kind of allows Bob to spend this 30 if Alice and Bob both sign something. And this one, Bob doesn't need Alice, but it's more in the future, right? So Bob can claim the funds much faster if he gets Alice to approve it. And if she doesn't, he can spend it, but kind of with a delay. And then this transaction is signed by Bob before they update the channel, right? So we have kind of a state machine where we have this situation here. We have a commitment transaction. So Bob owns Alice 30 micro bitcoins. And now Bob says, I will pay you 30, right? So Alice says to Bob, great, let's update it. Let's have a new commitment transaction in which you own me, the channel owns me 80 and you have from the channel 20. But before before I agree to this, you have to invalidate this one, because if you try to double spend to cheat me on this one, I want to be able to claim those funds, right? So she will not update this unless Bob gives her this output using this revocable, this bridge remedy, right? So she will say, I will kind of update the channel, the IOUs, if you give me this. So then I have a transaction I can put into the chain in case you want to cheat me, or in case you publish something which is out of sequence. Does it make sense? It's actually quite simple, but it kind of follows a bit of a state machine logic. So then, if nothing bad happens, if Alice didn't use it, then Bob could spend the funds, which means it's a normal situation. But if Bob published something out of sequence, then Alice could have used the transaction and kind of claim it. So the new commitment transaction is only signed if the other party reveals the revocation key, right? So we have those transactions every time we make a new commitment. We have those kind of revocation transactions we have to give each other. And before the new state, the new IOUs happens, we have to sign the other ones as well. So they have kind of a mechanism to claim the funds back if necessary. So red are all those transactions which normally should, should never happen. But if something happened, so let's say we are yeah, so here we have a situation where Bob actually published the initial transaction, the one he had 30, and then Alice used this one to spend the money that he was trying to claim. So she needs to do it before the timeout, otherwise she will lose the funds, right? So already here you can see that you have to have a mechanism which observes what is the current state of the channel to be able to react to a potential breach of the protocol. Okay, so in order to have this mechanism, we have to have the commitment transactions. We have to have a revocation delivery and breach remedy transactions. And every update of the commitment transaction requires those other revocation transactions to be signed. So we have quite a complexity for dealing with the state updates of the channel. And because we continually doing those, if we were to reuse the same keys, it would kind of leak kind of a lot of information of what is happening. So there is a suggestion of using hierarchical deterministic wallets, which allow both Bob and Alice to be sure that the signatures and so on are correct and kind of lead to the same source, but without reusing the hashes or reusing the keys. Okay, so that was to make sure that I can pay Bob and Bob can pay me without us cheating each other, right? So we have the funding transaction, which goes into the ledger, and then we have a sequence of commitment transaction updates, which update the IOUs. And apart from that, we have kind of a mechanism for claiming the funds if the breach happens, which using this kind of time lock contracts and the breach remedy transactions. So what are the HTLCs? Well, that's kind of a next step, because we need to have a mechanism for me to pay Bob and Bob to pay Alice if I want to pay her without Bob stealing the funds, right? So HTLCs are needed for a third party to be part of the payment along a channel when I don't have a direct payment channel to the to particular destination. All right, so there is work which is happening to kind of make it simpler and make it having certain trust and privacy guarantees, which I'm not gonna dive in here. There is a link in the slides, which is kind of hidden here, on the discussions which happen in this area. So I'm not gonna go into the details of the scripts neither, but what we covered so far is we have well, not so complicated mechanism for making transactions between two participants back and forth, keeping the IOUs within the capacity of the channel. And we know what sort of transactions do we have to exchange to have this working, right? One small problem with this mechanism is that it kind of incurs the penalty for submitting a state which is out of order, right? So if we have a particular channel and the publishing of the commitment transaction happens which is out of order, there is this unavoidable penalty where the party which is the one breaching the trust loses all the funds, right? So the penalty is actually for the entire amount of the party which did this out of sequence thing. Why it is a problem? It is a problem because if you're running a Lightning Network node, you might go offline for a while, right? And you don't know what is happening between the participants. And then once you go online and the participants kind of are updating the channel state, you might be out of sync of what actually happened with the network, like separate network, which they use to exchange their transaction. So remember, the only transaction really in the ledger is the funding transaction. All the other transactions are actually not recorded anywhere apart from the Lightning nodes, which are used to kind of negotiate all those additional transactions and signing, right? So if those two nodes go out of sync for some moment, then one of them might kind of publish the state which is actually wrong. Or if they try to, anyway, without going into kind of a lot of details of how the communication happens, the problem is that if you publish something out of sync unintentionally, not trying to cheat, it's just the kind of a nature of the IT infrastructure, you will be punished by losing all your funds, right? And that is undesirable in a situation where what would be desirable is you publish something out of order and then you say, sorry, I was off, and then you can publish something which corrects it, right? There is no correction. There's only kind of, you either are in sync or your funds are gone, right? That's kind of a little bit undesirable property. So more desirable would be if out of sync happens, there is a possibility to resyncing, and then the state channels is again is fine on both ends. So then the balance sheets can be kind of instantaneously updated, right? We don't need any interaction with the ledger. So using this protocol, I can open a channel to somebody and I can instantaneously send funds and receive funds as many times per second as I want. There is no real limit of how we're gonna do that based on the blockchain properties. The only limit is just off channel which we use to send those things, right? Yes, you have to do some signing, you have to calculate some hashes, so it's not like instantaneous, but it's not limited to the block mining or to anything to do with the ledger. So we solved, we have a solution to enable scalable peer-to-peer payment between two participants. And you could say, that's great, so we've solved it, right? Now we can send money to anybody using those channels. And that's correct. It's just a little bit hard to open channels to everybody you have to potentially pay funds to, right? You would have to open channels to all your friends. You would have to open channels to all the shops that you're dealing with, and so on and so forth. So you would kind of substitute the burdensome of putting individual transactions into the network. Now the burden is on the users to open all those channels. And then if you're buying coffee in a shop, okay, if you're buying coffee from the same shop all the time, it's okay, you can open a channel to them and pay them every morning for the coffee, and then there is only one transaction in the ledger, which is the channel opening transaction, and nothing else in the ledger, and then it's fine. But if you're buying coffee in different shops every day, you would have to keep opening the channels, and for opening a channel, you have to put a one transaction in. So what's the benefit? If I go to a coffee shop, to a new coffee shop, which I'm gonna use only once, I have to put one transaction in, so I may just as well put the payment transaction in, right? So, we don't know exactly how it will work. It's just that this solution works on a peer-to-peer basis, and opening channels with all those people you pay or receive funds from is a little bit infeasible. The other problem is you don't know how much the capacity should be. So again, with the coffee shop, it's fine because you know roughly how much a coffee costs. So if you want to say, I want to top up my account with this coffee shop for the next month, you can calculate how much buffer you have to have, and then you put your funds there, and then you sort of spend them without logging anything into the ledger. But for some things, you don't know how much you want to be spending, right? On the receiving end, whoever pays you have to set up this amount as well. So you have a little bit of a logistic challenge how to actually use it for payments. So that's the second part of the talk. How to make it that it works without everybody having channels to everybody else they need to pay. Do you have any questions for the first part? Yep. So the question is about miners mining a wrong block? What I don't understood.
Yes, so if the miners make a wrong decision,
Mm-hmm.
miss a wrong blocks,
Mm-hmm.
and but that action is not on purpose, but they will be punished with their available coins. So
Yeah, so in this system, the miners are not involved. In this system, only the participants, the people who put transactions in, right? If a miner picks a wrong transaction, it's not miner's problem. Miners just publish it, and it will become valid as long as the miners are concerned. So miners still get their reward. Nothing happens to the miners. It's only whoever has the funds locked with the channel will kind of lose the funds if they publish something out of sequence. Right, so the miners are safe. The miners have nothing to do with the publishing of the transactions. Yeah.
thank you. Sorry, maybe I misunderstand. Thank you very much.
Thank you. So it's a good question. So miners are basically when they see something in the mempool, and let's say they see two transactions competing with each other, and they pick the wrong one, the out of sequence one. The miners have no penalty. They just put it into the block, and it happens, and that's it. And then it's between me and Alice, or me and Bob, to settle that. Miners will get their reward, and nothing happens to them. Yeah. The person on the other end of the channel. So if I have a channel with you, and we agreed that you own me 5 Bitcoins, right? And if you publish something out of sequence which says that that you own me only 4 Bitcoins, then you will lose whatever the capacity you have in the channel because you try to publish something out of sequence. So it's between me and you, miners are not involved. Yeah.
Then will it have any potential for defeating the purpose of transparency? Because to begin with, like, the whole purpose of blockchain seems to be recording what has happened on the network, so that it can take care of the potential disputes. But if we just upload the final balance without knowing what has happened in between, then it's what we think about it might be working against the basic philosophy of blockchain. That's my question.
Yep. Okay. So it has 2 parts. The first part is more technical. The second one is more philosophical. So let's start with the technical first. So that the fact that if I have, let's say, I have a channel with Bob, and we set it up ourselves. Let's say I've put 5 Bitcoins and he put 5. At the end of the day, let's say I took 10 out of it, right? And he got 0. In the blockchain, what we will see is that we have a payment of 5 plus 5 and 10 going to me. That's what will be logged in the blockchain. We will not see what happened in between. We will not see all that back and forth between the but between me and Bob, right? And if the channel is open for a very long time, we can have channels open, for months or for a year. During that year, nothing will be visible in the blockchain. So that's how it will work. I will just digress to a side issue, which is at the very end, if Bob paid me the last, let's say it was 5 and 5 initially, we did back and forth, and in the last transaction, I was 9 and he was 1, and he paid me the last payment, right? So he was 1 and I was 9, he made me the last payment, and now he owns 0 in the channel, right? He can try to cheat me on this 1 Bitcoin, on whatever, because he owns nothing in the channel anyway, right? It's called nothing at stake attack, because if he has no funds locked in the channel, he can try to cheat me because, even if I punish him, nothing bad will happen to him, right? So that is a known situation with the original proposal, right? The second question was more philosophical. Do we require all the transactions to be to be visible in the Bitcoin, in the blockchain in general, in a public ledger? I don't know. You might say yes, that's the kind of the design decision. You may say no, like whatever I'm dealing with Bob is nobody's business unless one of us is trying to cheat the other, and therefore it will be visible, right? If I'm dealing with Bob during the duration of the channel opening, and then Bob tries to cheat me, that will be visible in the blockchain, that he tried to put something out of sequence and he was punished. That will be actually in the ledger. But if none of us try to cheat each other, this is not there, right? And the other aspect is that we have other ledgers. We have Dashcoin, we have Monero, we have Zcash, which actually make transactions invisible to third parties. They try to hide what actually happens in the blockchain from a third parties to see what is not relevant to them. They can validate that things follow protocol, but they cannot see the balances, they cannot see the amounts, they cannot see actually who was sending money to whom. And some people say this is more like what it should be. It's more privacy preserving, more anonymous, and that's what the true cash properties are, right? So this digital cash, I showed this email at the beginning, and it said digital cash, right? When you're dealing with cash, it has certain properties. One is strong anonymity. When people have cash in their pockets, nobody sees how much money they have. When they pay with cash, nobody else can track it, can see it, right? It's different to using cards like Visa or your bank transfers. But with cash, you have a very strong privacy properties which this digital cash is trying to mimic. So for some people, being kind of anonymous and not visible to the ledger is a desirable property. And most of the Lightning Network developers feel that way. They feel that this enhanced invisibility, privacy is a desirable property. I don't know. So I think it depends.
So it should be understood as the premise that enhancing privacy is a good thing. That's kind of an axiom, and taking that axiom is true, then this is the desired property. That's how I can understand it, right? Yeah.
I would say so, yeah.
Okay, thank you. Thank you a lot.
Thank you. Yes?
Yeah, it seems to me that you need to go through quite a lot of pain to get this state channel idea to work in the Bitcoin context. And why should anybody care other than a Bitcoin maximalist? I mean, the rest of us can do all this sort of stuff a lot easier on Ethereum, for example.
That's correct. So there, again, two sort of answers to that. One is work on this kind of led to some innovation in terms of atomic swaps and being able to do certain atomic operations between participants on a kind of a protocol level, and that's a good thing. So there are some lessons learned and some protocols and properties which can be reused in different contexts. So this work is worthwhile even if the final result is not used as a whole, because it leads to some innovations on the protocol level of how to achieve some properties, some outcomes using the technology that we have today. The other thing is that Ethereum is experimenting and was experimenting with off-chain transactions as well. This technology is applicable to other blockchains almost the same way. So being able to transact without logging everything into a ledger is a property which, Ethereum could benefit from as well. It might need to be done slightly differently on the script level and the protocol level. Ethereum has much more capabilities of expressing certain things, but I think the work is kind of valuable to wider context than just Bitcoin. In particular, it's I've asked the first speaker what is the way to scale kind of blockchains. And his answer was that in the context of permissionless, open, anonymous ledgers, the only thing currently working is proof of work. And that's not good enough for scalability. We know that. There are other mechanisms, potentially, but we have to look into mechanisms which actually do scale those permissionless, anonymous ledgers. And kind of working towards the off-chain transactions is one potential solution. I don't know if it will be the solution, but I think it's worthwhile looking into it. Does it answer your question? To some extent? I totally agree with you on that one, yes. Any other questions? All right, so let's continue a little bit into the second part, which is how to do this network. So all we talked so far was bidirectional channels between two participants. There is no concept of the network yet. Okay. Yes? Yeah, okay. So if I only have 5 minutes, then okay, I will skip the very simple scenario because I think we kind of understand the concept of payment and receipt. So what we would like to have is we would like to have a system where the person in the middle is obliged to follow the protocol in such a way that they cannot run with the money. So if we have three-party situation where I have a channel to Alice and Alice has the channel to Bob, so I'm here, Alice is here and Bob is here, and now I want to pay Bob, and without setting up a direct channel, because I already have a channel to Alice and Alice already has a channel to Bob, then we would like to have the ability to update these IOUs between us in such a way that the middle person cannot, run with the money. So how we will do that? We will do that with Bob issuing an invoice and giving it to me. And then I will use some information inside this invoice, including a pre-image, like a hash of a secret that only Bob knows. So Bob generates a secret, which only he knows. He hashes it and gives me the hash. I will prepare the transaction telling Alice, here is 1 Bitcoin. You can claim it if you know the image which hashes to this hash. And you will know it if you pay Bob, because Bob will have to use it to unlock the payment you will do to Bob, right? So I'm sending Alice a transaction saying, here is 1 Bitcoin. You can use it if you will know this secret. To know this secret, you have to pay 1 Bitcoin to Bob, because when Bob tries to claim his Bitcoin, he will reveal that secret. Therefore, it will be revealed, and therefore you can use the coins yourself. So this is a protocol called HTLCs, hash time locked contract, which basically makes kind of a multi-party payment possible because the party in the middle cannot really use the funds until the final party reveals the secret, right? So I will skip all those slides. So it's called hash time lock contracts within the payment channel, which means now we can follow multiple hops and nobody in the middle can use the funds until the recipient claims the funds and reveals the secret. And then once the secret is revealed, each subsequent hop can claim their funds for themselves. So I paid Alice, and Alice will have my coin as long as Bob gets her coin, right? So that's one issue left. Then we have to have this format, so the talk goes a little bit into what we need to have those HTLC actually work. And it's the specification called Bold 11, which explains all those things. And then there is a final thing. The final thing is, is this one. So routing. So how do I know that Alice is connected to Bob if I want to pay Bob, right? We have to solve the problem of finding the routes and actually routing the payments through those HTLCs. And there is kind of an ongoing work of how to make this possible. So I will stop here. We have maybe 1 more minute if you have question.
Yeah, so I'm just wondering, even with these sort of this network style of payment, just about the total amount of collateral that needs to be locked up to make this into a viable payment system.
Yeah,
I mean, this Lightning's now up and running, and are we starting to get some statistics on how well it's working with respect to that, or is it still too early days to get some empirical evidence on this?
It's a little bit early days. Because of this technology still being very unreliable, and also because we don't have this mechanism to roll back the incomplete state, people tend to use it for small transactions. So the actual locking is not that big. Philosophically, if you think about it, if you have bitcoins in your wallet and you're not doing anything with them, you may as well lock them into a network of payments which they be doing something for you, and you might be earning fees, right? So having bitcoins in your wallet, which are in the ledger, and having things locked in the channels, which are also in the ledger, philosophically is kind of the same, right? But it is a valid point. And
yeah, I mean, so the question is, is there a business model here to be a liquidity provider, or is the amount of liquidity that's going to need to be provided just too much for it to actually work?
Yes, that's right. So there are some business models, proposals which are being explored, and there is some interest from the financial institutions to kind of be part of the network and provide, know your customers, anti-money laundering, and the financial liquidity which is necessary for the merchants and for the payments. So I'm not that familiar with this business aspects of this work, but I know there is an interest and there is some work happening in that area, yeah. Okay.
Yeah, so I'm actually wondering, so for participants in the Lightning Network that pay a lot more Bitcoins than they receive, or receive a lot more Bitcoins than they pay. Let's say, imagine I own a coffee shop, and lots of people pay in Bitcoin, but I immediately sell them for dollars. I don't really spend so much Bitcoins. Or the big Bitcoin exchanges that they don't support Lightning Network, so I have to.
Yes.
So in that case, I'd be receiving or paying lots of Bitcoin and not getting any back, and that means the channels will be continually closed and open. And would this cause a scalability challenge if I don't have enough capital for huge channels?
Of course, it's an excellent question. It's actually part of the work that I'm directly working with. So if you are kind of a hop where you're mostly spending money, what we try to do is we try to find routes which kind of go backwards, so you get the money back because you're part of the route which goes somewhere else, right? So if you have two, let's say, shops, and they both have kind of a lot of inflowing money, maybe we can link them in such a way that actually route the payments through the other one to kind of refill it, to rebalance it, without closing and opening channels. So we try to find ways for the funds flow to balance the characteristics of you spending and receiving money such that it balances off. Yeah.
Got it.
Thank you.